Okay. Let's start. Good afternoon, everybody. How are you doing? Good. Good. I hope that you are very, very well. Let's start today's lecture. Please answer these two questions. It's related to the previous lecture. We will have a lecture about energy, different types of energy, conservation of the energy, and also the kinematics of a rigid body for today's lecture. Did you answer the questions? No. No. Those are easy questions. Now I can see. First question until now, 74% answered it correctly. Second question, not good. Not now, it's 57%. Do not try one of your answer randomly, then the next one or your neighbor answer based on your answer. Do it by yourself. Good. Can you start to solve the questions? Yes. Yes, good. First question, 72% answered correct. Good. That was an easy one, but still 28% needs to study more. And second question is 69% answered it correct. 30% didn't answer the question correctly or gave the incorrect answer. we started to talk about the work. You know about the work? Work is the force multiplied by displacement as you learn in the physics. But I show you how to find the work in terms of the mathematical expression. And I explained that we can write the work, the differential amount of the work, if a force applied to the particle using this equation, F dot dr. Or this is how we can find the differential amount of the work using the force of F moving dr or displacement along the curve. And you remember this one can be written as the absolute value of F, absolute value of the dr, multiplied by cosine alpha. Alpha is the angle between the force and displacement. And for the first question, because the force, it is perpendicular to the displacement, alpha will be 90 degrees, means that cosine alpha will be 0. It means that the amount of the work done, if I just find this one from S1 to S2, or this is the work, it will be 0. C is the correct answer. And also, you found that not any type of the work, any type of the forces can do work. The force along the displacement can do a work. Forces that is perpendicular to the displacement, the work of this force is 0. For the second question, if a particle moves from point 1 to point 2, and the work done by a particle by the force of the Fr, Fr is the resultant force. As you can see here, we found the component of this force along a tangential and normal direction. Sigma Ft is the summation of the forces along the tangential direction. Summation of the force along the normal force, it is called sigma Fn. And also, because sigma Fn, it is perpendicular to the direction of the motion, or ds. And also, you answer this one correctly, you can easily eliminate position in option C and D. Fn, those ones do not do any type of work because they are perpendicular to the direction of the motion. The only term can do work is sigma Ft. By which one? The first or second one? Because sigma Ft, it is along the direction of the motion. It should be positive. You do not need to just remember the formula or something. You'll see. Just if sigma Ft, it is in opposite direction, this answer will be correct. Is that for the second question, first, this one is correct, or A is a correct answer. Any questions? No questions? Yes?
If it was moving the other way, is that when it would be negative?
Yes, if it's moving, yes, exactly. Moving on this direction, but the force will be in this direction, it should be negative. Yes. Good question. Other questions? I want to give you an interesting news. Can I move to the next slide? Yes. We will have exam 2 on next week. Just stick to the plan, but I want to remind you. Next week, Thursday, we will have exam 2 on the class time. Please bring yourself a pen, pencil, and a calculator. That's it. And also, Similar to the exam one, it's a closed book, closed note. I will provide the equation sheet. Equation sheet is uploaded in the week 8. I just uploaded now. And also the material that's covered, it is until next class Monday. Okay? It's a cumulative exam. Any questions? There's no question. Any question, guys? Similar to the exam one, there's 5 questions. Similar to the homework. Please practice what I solved in the classroom. The last question I gave you for the exam one, I think that most of you it was your first time that you can see this problem, how we can solve it. Please practice problem I gave and homework. I just put the solutions. Also, I put the practical examples for you. Those are related to the exam too. And you will see similar questions will come. Yes? What? Yes, the first question, as I mentioned, similar to the exam one. How was the exam one? Exam one, first question is a multiple choice question. This is the reason I always put questions in the first class and ask you about the review session. Similar to the exam one. Any questions? No? So far, so good. Can I move to the next slide? Yes. Continue our lecture about work, and now I'm going to talk about the conservative forces. What type of force is called a conservative force? Force that if you calculate the work of the force, this work is path independent. Or using this integral. This integral is the integral for a closed path. As you can see here, if I find the work of this force F from A to B plus the work of this one from B to 1, if this integral it is 0, this type of force it is called conservative force. Now, do you guess what type of forces? Or just can you explain any type of forces that you think that it can be a conservative force? Which force do you think that will be conservative force? There are lots of forces we have. Damping force, normal force, weight, frictional force, spring force. Which one? Or other type of forces? Yes? Weight. Weight. Weight is one of the conservative forces. Another one. Yes? Friction force. That was my second question. I do not answer it, but let's go to the next one. I can answer. Other students. As you mentioned, the weight or gravity and spring force. These are two forces that we can call as a conservative force. How? Let me prove it. Okay. For example, for gravity, you learn that if you remember, the work of the gravity or weight from point 1 to point 2, it was minus W weight y2 minus y1. That y2 minus y1 is the kind of difference between the elevation along the vertical direction. For example, this one is going from 1 to 2. From this one, this datum line, this is the y1, this is the y2. If this particle has a weight of W, these equations can calculate the amount of the work done by the weight. Now, for this one, to find this for a closed path, for example, from A to B, if the particle moves from A to B, then moves from B to A, and their height and elevation from this datum line, it is YA and YB. Now, using this integral, as I mentioned, the amount of the work from A to B plus the amount of the work from B to A, if this one is 0, it's a conservative force. If this one is not 0, it's a non-conservative force. Now, using this equation, from this, it is minus W. The elevation of the second point means that YB minus elevation of first point plus, now return back to the same point, means that plus weight elevation of second point, it is A, YA minus elevation of the second point, or first point, sorry. Now, let me sorry. Yes, Rodney. If we calculate this, it is minus WYB plus WYA minus WYA plus WYB. This cancel with this cancel with this. It is equal to 0. Now I show to you that the weight is a conservative force. You can do this one for a spring force. If you remember, for the spring, the amount of the work done by the spring is 1 over 2k x2 squared minus x1 squared. If you do this one also, you can find this one is a conservative force. Now, any questions? No? I have a question. Now, do you think that the friction is a conservative or it's a non-conservative force? To answer your question. And also your answer. Friction is a conservative or non-conservative? What do you think? Yes?
I would say no, because it's going to lose thermal energy.
Okay. I collect your answer. That's good. Yes? Other students? Yes or no? Is it conservative or not conservative? Which one? Yes?
There would be non-conservative because different paths would have different frictional coefficients.
Exactly. Frictional force is a non-conservative force. Okay? And different paths of this one, this depends to different factors. friction is a non-conservative force. Got it? Now, the reason that I just explained about the conservative force, I want to explain that a conservative force causes a potential function. It means that a force, a conservative force, it has a potential. This one also, it explained in my previous proof that the work of the weight on different paths are similar. Now, because a conservative force, there's a potential function for the conservative force. I want to introduce the potential energy. Okay? Now, what you learned before, I think that most of you know about potential energy. Potential energy is the measurement amount of the work of a conservative force. A non-conservative force, such as friction, cannot have a potential energy. A potential energy means that, for example, if this one release the ball from some height, this one will reach to the ground, it has some potential energy. Or if you compress the spring or stretch the spring, also a spring has a potential. All of you have potential. Okay, and this is here. Means that for a potential energy, I use the V based on this reference. To show the potential energy. Also, it's a type of energy. The unit of this one is joule. This type, it consists of two potential. One, potential energy because of the gravity. I call this one Vg. G is coming from gravity. And also, the potential energy because of elastic spring. Why they have potential energy? Because spring and also gravity, I show you that they are conservative force. Got it? Okay, move to the next slide. Now I want to find these two potential energy because of the gravity and also the potential energy of the elastic spring on next two slides. First, the potential energy because of the gravity, we can find Vg is the potential energy because of the gravity, and we can find it using this equation. Vg equal to positive negative weight multiplied by the W, that is height, that is measured from the datum line. This one is measured from datum line. You can select any lines as a datum line. For example, when this particle moves along this curve, it moves from this position to this position, and there's a weight applied at the datum line because y it is 0, there is no potential energy. But above of this datum line, the potential energy is positive. Below of this one, the potential energy is negative. Okay? I just explained it before. For example, if this surface is a potential line, it's a datum line, and just I hold this one, above of this one. If I release this one has an energy, it's a potential energy. However, if this one is the below of this line, I want to bring this one up. I need to spend some energy. This one needs some energy to bring up, and it comes up to the datum line. This is the reason below of the datum line is negative, above of the datum line is positive. Can I move to the next slide? This is explanation. Also for elastic potential energy, one example is the shock absorbers. Shock absorbers that is used for vehicle suspension systems. And these have a potential energy. How we can find that? Using this equation. To find the elastic potential energy for such as the shock absorbers, the elastic potential energy we will use VE. E is coming from elastic. Now, for a spring that has a stiffness of the K, if started to stretch the spring with the amount of S, you will see that S it is measured from on stretch position. Also, if I compress the spring, both S positive or negative 1, the potential energy will be 1 over 2K S squared. From here, because this one is starting and also measured from on the stretch 1, this one is S. However, sometimes some spring has a length. For example, L0. Then, when I stretch this spring, the length becomes L. S will be the difference between L and L0. Also, you can see from this one, the potential energy because of elastic spring, it is always positive. When I stretch the spring or if I just compress the spring, the potential energy will be positive, always. The only reason and also only case that this potential energy will be 0 when started from unstretched position. Always means that spring has a positive potential energy. Got it? Those are easy. I think you know the all, but I have to just use it. Now, before I move to next slide, I want to ask you, what do you know about the conservation of the energy? Can you explain what is called a conservation of the energy? All conservative. What is called a conservation of the energy? Any person? What does it mean that the energy will be conserved? Yes.
It stays in the system.
What?
You say it stays in the system.
It stay in the system. Is it right? Yes. Yes. Yes.
Say conversion between type of energy and it loses some over time.
The first part was for the second part. Conserve doesn't lose because all the forces will be conserved. There is no waste of the energy. The first one is just one energy will be conserved to another one. That's correct. However, as I mentioned, the conservation of the energy is that the summation of the potential energy plus the kinetic energy at state 1 will be equal to summation of the kinetic energy plus potential energy at state 2. The example is this pendulum. Consider that there is no friction of the air, and also this link is the inaccessible. It's just moving on an ideal environment. If I release it at this position, it has a maximum potential energy. It is converted to the kinetic energy. Then the kinetic energy convert to the potential energy and go back up, down, up, up. However, in reality, if you do this one in the just this air, after some time this will be stopped. Why? Why the pendulum in real environment will be stopped after some time? Yes.
Energy will eventually be lost over time due to friction in the air.
Yes. Because the friction of the air just get wasted, and also this energy we can convert it, but some portion of the energy will be wasted during the kind of because of the friction of the air, or because of the elasticity of this spring or this core. Now to show you one example. If there's a pendulum, I hold the pendulum. Hold the pendulum means that velocity will be 0. Then this height, if I measure its h, for example, from this ground or this datum line, this pendulum has a mass of m. If I release this pendulum and reach to this point that has a maximum velocity, my question is this velocity depends to the mass of the pendulum or not? What do you think? Again, if I release a pendulum with a mass of m from height of h at this position, that the velocity is maximum. If I calculate and find this velocity, do you think that this velocity depends to the mass or not? For example, if I release one pendulum with mass of m and release second pendulum with a mass of 2m, their velocity, maximum velocity will be same, less, great. What do you think? First question, just answer. Does it depend to the mass? Does it depend? Yes or no? What do you think? What do you think? Lawrence? No? Other students? I think that you like to solve examples instead of answering 0, 1, or yes or no. Yes? If you like it, I can give you those. I think that this one is much easier. Yes or no? No. Who mentioned yes? Raise your hand. There's no grade, guys. Raise your hand. What do you think? Yes? Others still mentioned no? No. Raise your hand. No. There's no option. Just between, there's no between yes and no. Or only yes, only no. No. Let's see this one is correct or not. If I use the conservation of the energy between state 1, this is state 1, or position 1. This is state 2. This one is the kinetic energy. What is the kinetic energy? 1 over 2 mv1 squared. The potential energy at this point, it is, because if this, I consider this line as a datum line, it will be positive WH. How I found this one? From W. Y2 minus, sorry. The potential energy, it is positive WY. Y is measured from the datum line. Just here, Y is H, equal to 1 over 2 mv maximum velocity squared plus the WY. How much is the potential energy at state 2? 0. It is 0. Because this one is 0. Also, because it released from rest, this one also is 0. From this equation, you can see WH equal to 1 over 2 mv maximum squared. Or this one is mgh equal to 1 over 2 mv max squared. You will see masses cancel. Means that the maximum velocity will be square root of 2gh. The maximum velocity only depends to the gravitational acceleration and h, the height that is released from the datum. Got it? Interesting. Then move to the next slide. Yes. Example. Very interesting example. There's a 40-kilogram hammer. It is lifted at the position 1 and released from rest. It falls and strikes a workpiece with at the position 2. The spring constant is 1500 Newton per meter. And the spring, it is on a stretch at the position 2. Neglect the friction, use the conservation of the energy to find the hammer's velocity at position 2. This type of example is type of application. It's used for forging of the big parts. Let's write this one and think, and then I will start to solve. Okay, let's start to solve this problem. The mass of the hammer is 40 kilograms. This is given. At position 1, it is started and released from rest. Means that the V1, or the velocity at position 1, it is 0 meter per second. Then spring constant, it is 1500 Newton per meter, and the springs are unstretched when the hammer at this position. Look, at this position, these springs are unstretched. Means that the initial length of the spring, it is 300 millimeter or 0.3 meter. We want to use the conservation of the energy. If in one problem mentioned that you have to use conservation of the energy, you have to use same method. Means that for this problem, the solution will be use the conservation of the energy. What's the conservation of the energy means that T1 plus V1, the potential energy at state 1 or position 1 equal to T2 plus V2. This is called conservation of the energy. Now, what we are looking for to find, we are looking for to find the velocity at state 2, or at position 2. Okay. Now, one thing before I just move to solve this problem, I want to mention that do not confuse the conservation of the energy with principle of the work and energy. That's you are working with your homework. The principle of the work and energy means that the amount of the work done from state 1 to state 2 equal to delta T. For example, in the exam, when I mentioned use the conservation of the energy, you cannot use this one. Even though we can use this one to solve this problem. And it's possible. But we need to use, and you have to speak to the method it is mentioned in the problem. Then, can we move to the next slide? Using this equation, T1 plus V1 equal to T2 plus V2. This is called conservation of energy. What I do usually, I write them look like this. T1 equal V1 equal T2 equal, and finally V2 equal. I need to find each of these ones. First, T1, it is 1 over 2 m V1 squared. How much is the velocity when this one it is released? 0. This is 0. This is 0 joule. Now, V1, it is the potential energy because of elastic spring at position 1 plus the potential energy because of the gravity at state 1. Now, if I consider this line as a datum line, you can also consider here as a datum line. It's up to you. Now, the potential energy because of elastic spring, it is 1 over 2 K S1 squared plus W Y1. Y is because of this as a mass, and this one, it is from this height. This is the potential energy because of this hammer. These are the potential energy because of elastic springs. Now, if I equal this one, it is equal to 1 over 2 K. It is 1500. Now, how much is this one? Can you calculate? How much the spring at state 1, it is elongated or stretched? How much? 200 millimeters. Yes, correct. 200 millimeters. To find the S1, I will write here. S1 it is the final length of the spring minus the unstretched length of the spring. Now, L here at this position, it is 1. Okay? The length of the spring, if you calculate it, is 500 millimeters. This is 300. This is 400. And from this, you can find this 500. This equal to 500 minus the initial length or unstretched length of the spring. It is 300. It is equal to 200 millimeter or 0.2 meter. Then I put this one here, 0.2 square plus this one. Plus the weight of the hammer, it is 40 multiplied 9.81. The height from the datum line, it is 0.4 meter. Yes.
Isn't the energy of the spring double because there's two springs?
Exactly. I want to ask this. The reason I just put this space here, I want to see that who knows and also detects my mistake. Right. Yes. There are two. Got it? There are two springs. Now, if you calculated this one, and this will be 60 plus 156.96. If I'm calculating this one, 50 plus 156.96, it is 216.96 joules. Then, at the state 2, the kinetic energy is 1 over 2 m V max squared, or 1 over 2 m 40 V max, or maximum velocity at state 2. Sorry, what's called V2. Just confused with previous. Then, the potential energy at state 2, this is potential energy, not confuse this one with the velocity. This is called potential energy. I use the italic small one for the velocity. Now, if I write this one, it's a potential energy because of elastic spring at state 2 plus potential energy because of the gravity at state 2. This is equal to 1 over 2 k S2 squared plus the weight multiplied by Y2. Now, how much is S2? 0, right? Because it is unstretched at this position, S2 is 0. How much is Y2? 0. Also, this is 0. This is also equal to 0 joule. Now, we have everything here. If I put into this equation 0 plus 216.96 equal to 1 here. This is equal to 20 V2 squared equal to 20 V2 squared plus 0. If you calculate the velocity, will be 3.29 meters per second, and this is the answer. Got it? Similar procedure you have to repeat for the homework that I will give. It's exactly what I did in here. Find the kinetic energy, potential energy, state 1 and state 2, equal them, and find the unknown. Any questions? No? No questions? No question 1? No question 2? 3. 5-minute break. Yes. Sure. No. This one is this is a 300. It's a 300 squared plus 400 squared divided by 5. this is one, this is 300, this is 400. This makes 200, sorry, it's really, yes, 300 plus 400. And we will find just this is right hand. Okay. Oh, yeah. Yes, Toby.
Dr. Bachman's there tomorrow. He hasn't been in his office in the past 2 days. I've checked it. I need to talk to him about trying to get class out of category. So I need to look at the syllabus.
Dr. Marcus, I need a meeting.
Okay, so he's here.
No, not yet. We have an event. Stuff Detroit person. I will go to the Detroit person. If you want, I can. Did you send that email?
Yeah, I sent an email yesterday. I just don't know if he was finished. I want to see.
No, I'm not sure he will return back or not because the event will be here up to 2 p.m.
Okay.
And it started from 8 p.m. to 2 p.m.
Okay.
I think that might be, I'm not sure, but we will come next morning.
Okay, he'll be here.
Yeah. I think that he really, if you have any questions, also you can take the virtual meeting.
Yeah. Okay.
Okay. For example, just send an email. Also, I will mention when I just visit.
Yeah.
Okay.
Okay.
Can you send me a follow-up email tomorrow?
Yeah.
Now, set up those ones.
Yeah, see if he replies. I just say, yeah. I'm trying to take fluid dynamics out, and it's a weird situation.
Okay, you want to take the fluid mechanics out of the fluid?
Yeah, I have. It's weird because I'm an MEE, so I got in a weird spot where all my classes like overlap. So I have to take it out before the winter. So.
Let me. I just mentioned that also.
Okay.
I was asking to reply.
Yeah, it's not too much of a big deal because I can still register for all my classes without it. I just didn't know if you have to really be in that.
No, I do not think so. That I will come to this.
Okay.
I just checked in his office 1 hour ago before class. He weren't in the office.
Okay.
But I know that he will come tomorrow
Okay,
because we are on the same desk.
Yeah, I was say, I'll just sit down. Yeah, worst case scenario, I'll just sit down with him Monday after I register or something. Maybe after our class or something.
He is. I think that most of the. Just send me a follow up.
Yeah.
Follow up.
Okay.
After the class, just make sure you send me.
Yeah. Yeah.
And then if he doesn't respond back, send me a follow up.
Okay.
Okay, good. I will talk to you.
Thank you.
I think the rest of it yesterday. I think so. Yeah. No, he changed it, it's class now. I think he forgot to do it.
Oh my God.
was like, that's the worst possible time. Okay, did you just do the final thing? The final? Good. I mean, you can. Yeah, you get. Okay, this one's a Thursday. Yeah, which is fine. I just didn't want to stay here. Oh, that's it. Except for, of course, surgery. I got no. Oh yeah, math too. I got math, but recovery stats. Two five eight zero
Okay. Let's resume the class. Any question for first part? No questions? Okay. Now, we want to wrap up the topics related to the particles, and we move to the another type of the body is called rigid body. And for a rigid body, when it's in the planar motion, we want to analyze the rigid body and find the velocity acceleration of the rigid body for different cases. And for today's lecture, first I will show you the applications why we need to use the rigid body. Then I will show you different type of the motion for the rigid body. And for a translation and rotation about the rigid rotation about the fixed axis, I will show you the equations how we can find the velocity and the acceleration. Now, the applications why we need to learn about rigid body motion is related to vehicle dynamics, robotics, aerospace engineering, biomechanics, and structural engineering. For example, in vehicle dynamics, when you want to find, and also, it was a part of one question I gave you for the homework. This type of system, it is prevent the skidding by controlling wheel rotation. And also for the cars, these are related to the wheel dynamics, and these are the reasons why we need to learn about the kinematics of the rigid body. In robotics, for example, robotic arm in the car assemblies, these are type of the rigid bodies, or in surgical robots, or in aerospace, Boeing is a one, or in space, Mars rover. Or in biomechanics, those bionic prosthetic legs, or in constructions, towers, excavators, in machineries, CNC machines, in structural engineering, those earthquake-resistant buildings. Those are the examples of the rigid body that we are interested to learn about their dynamic and their motion. Okay. Do you remember how I introduced a rigid body. What is the rigid body? What type of body is called rigid body? Yes, Ali.
A body whose shape changes negligible compared with overall motion, or a rotating wheel or moving car body.
Exactly. Rigid body compared to the particle, the size and shape, it matters. We have the size now. Also, for the rigid body, we consider the rotation. You never heard from me that just I called and also I explained about the rotation of the particle, because the particle doesn't have size if it's rotating. How we can find the forces or those things. But here, because this rigid body has size and shape, we will consider the rotation. And for rotation of this one, we can find the velocity and acceleration of the body in any places, any point inside of the rigid body or out. Examples related to the mechanics, design of gears, cams, spring, those are examples of the rigid body in analysis of the motion. We start the rigid body motion. We limited our study in planar motion. Planar motion means that, for example, if we have this reference plane, the motion happens, for example, on this plane or one plane that is parallel to this one. Okay? For example, here the motion happens here, or here the motion happens here. We limited our study and limited our kind of course in planar motion. Then, first type of the motion for a rigid body is called a translation. Translation means that rigid body consists of several particles. Not one, it consists of several particles. If I selected two particles inside of the rigid body, such as A and B, this is the rigid body. And I track the position of the A and the B during the time. For example, this is at time t, this is at time t prime. If I track the position from t to the t prime, and this is moving along this line, track the position, for example, during different time intervals. And also, track the position of the B during the different time interval. And I just connect those points together. I can see that the path of the A and also the path of the B, they are on straight paths. Okay? You learn about this type of the motion. It is called rectilinear. Also, because the paths of these two particles, they are parallel to each other, this is called a type of translation. Means that this one is called a rectilinear translation. Similar to this one, if these 2 points move along a curved path, it's called a curvilinear translation. Now, one example is a rocket car, just moving, and all bodies, it has a rectilinear translation if moving along a straight path. Also, for a curvilinear one, when this one is moving along this parallel swinging plate, just as an example for a rigid body with curvilinear translation. This is one type of the motion for the rigid. This is an explanation what I just explained. And translation occurs if line segments they remains parallel. Also, this motion is called rectilinear. As you know, all points move along a straight line. It's called curvilinear if all motions, all particles move along a curved line. In one sentence, here. These are moving a straight path. These are moving along a curved path. We'll see A is moving here. B also is moving here. These are parallel. This moving here, this moving here. These are parallel. Okay, move to the next slide. How about the rotation? A type of the motion for a rigid body is called rotation. A rigid body, you know about the rotation. If this is the rigid body and this is rotating about this axis, if I track the position of one particle inside or outside of this rigid body and track the path of this one during the time, I can see that this path has a circular path. If you find a rigid body that's track the path of the particle and this one moves along the circular path, this rigid body has a rotation. One example of this one is a pendulum. You will see that this one has a rotation. Then, the next type of the motion for the rigid body, this is the second type of the motion. The next type is general plane motion. It is the combination of the translation plus rotation. If you have both translation plus rotation, it's called general plane motion. For example, this one, first translated first, then it rotates, look like this. Or it rotates first, then translate. This is called general plane motion. Now, one example. This example. There's a piston connected using a link to the wheels that rotate simultaneously. There's also a link between this rotating wheels and also a crank. I want to show you different type of the rigid body motion for this example, as you can see. Now, first, this wheel and also this crank that I show you with the red color, they both have a rotation. If you disassemble all of this one, and you will see just this wheels, it rotate about this pin point, and also this crank, it is rotating, look like this. These are two examples of a rigid body that has a rotation. Then, this piston, yes, it has a rectilinear translation because the motion, it is limited to move along this direction. It has a rectilinear translation. Also, this link, because both ends connect to the bodies that rotate, it has a curvilinear translation. And finally, this one. This link has a general plane motion. Why? One end of this one, it has a rotation. One end of this one, it has a translational motion. This link has a general plane motion. For the remaining of this course, you will see that how we can find the kinematics of the rigid body, and also for a translation, for a rotation, and also the combination of translation plus rotation. Any questions? Can I move to the next slide? Now, what I'm going to teach the rest of this class. First, for a translational motion, and also for a rotation. For both type of the motions, I will explain about the kinematics of the rigid body when it has a translation motion. And also, I will explain about the kinematics of the rigid body when it has a rotational motion. What I want to do, for example, for a rigid body that has a translation motion, I want to relate the velocity of any point inside of this particle together. Also, for a rotation, what I'm going to do today, I will explain what is the type of the rotation, what is an angular velocity, angular position, and angular acceleration, and how we can relate them together. I'll relate this with this, or this with this, or vice versa. This is the remaining of today's class. Now, first for a translation motion, this one is the type of translation. Okay? Then move to the next slide. If this one is the rigid body, I want to relate the position of the A with position of the B. This one, the blue one, it's a rigid body. Now, I will introduce two coordinate system. It's a fixed coordinate and also translating coordinate. Translating coordinate, it is attached to the rigid body. The fixed coordinate, it is fixed. It doesn't move. But this one, it moves to the rigid body. Now, does anybody remember where I explained similar contents before? Do you remember? Does anybody remember? Let's help you. Did you remember about the independent motion of the particles? Or how we can use and relate the position of two particles that they have an independent motion. If you remember, similar to this, I explained that. Look like this. This is a Lake Michigan. And these are two boats. They are moving separately. And we can relate their position using this vector. Now, if RA and RB are the position of the A and the B from a fixed point, for example, there's a fixed observer here. Fine. Now, this A and B now is the two particles inside of the rigid body. The rigid body has several particles. Then, we can relate the RA and RB using this triangle. Or we will use a relative position vector RB with respect to A, and RB will equal to RA plus RB with respect to A. Now, next one, I want to relate the velocity of the B with velocity of the A. How? How we can relate the velocity of the A with velocity of the B? But I have the position equation. How can I find the velocity relative equation? Yes, derivative. If I take the derivative of this one with respect to time, I can find this equation. The derivative of RB with respect to B is VB, and the derivative of RA with respect to B is velocity of the A, and this term is the derivative of the RB with respect to A with respect to time. Now, my question for you. What do you think about this term? The change between the relative position of the A and B for a rigid body with respect to time. How much is this term? Or what this term is called? This term. How much is it? It shows that the relative position of them between A and the B for the rigid body during the time, how much is it? Does it change? Yes.
Zero.
It is 0. Because it's a rigid body, okay, look like this. I cannot change easily the points between these two ones. Also, if I push this one, means that change the position between them, it is always constant. The distance between them, it is always constant. And this expression, it is always 0. Why? RB with respect to A, it is always constant. Then, as I mentioned, because this RB with respect to A is constant, the velocity of the A equal to velocity of the B. Means that for a rigid body, when it has a translational motion, the velocity of any points inside of the rigid body, they will be equal. Also, their acceleration also will be equal. One example, just there is a car with several passengers. It's a type of kind of a rigid body with several particles. When you are moving and also driving on a straight path, all of you have a translational motion. All of you have a same velocity, same acceleration. If you do not have same velocity and acceleration, what happens? One of you jump from the window. Okay, now what we found here for a translation motion for a rigid body, the velocity of any points are equal, and also their acceleration also will be equal. This is the conclusion from this. Then, can we move to the next slide? No. You have a question? Any question? Feel free to ask. Got it? Okay. Now this is the translation. How about the rotation? For a rotation about the fixed axis, it's a rigid body that rotates about this axis, okay, with the angular velocity and angular acceleration of the alpha and angular velocity of the omega. Okay, now for a rotation, as you remember, I explained that for a rotation, if I follow the path of one point on a rigid body, it moves along a circular path. Or if just I connect this point on the axis of the rotation to the point P, and when this one is rotates, it covers this circular blue shade. Now, for a rigid body that it is rotating about this view is the top view of this. Means that the point P, it is rotating on a circular path. And we use theta, okay, to show the position of the point P for a kind of from a reference. This point, or theta, it is called angular position. And it's measured from a constant or a reference. If you remember exactly for a particle, when it has a rectilinear motion, starting from origin, when this particle moves to point P, we use R to show the position of the particle at point P. similar to this one, when a rigid body it is rotating this point or any point, we can find and measure the position of the point P from a reference using theta. Theta is called angular position. For this case, for a particle, it's called position. This is angular position. It's for rotating of the body. And theta is an angle. For example, at here, it is pi over 3. Then, if point P moves to the point P prime for a differential amount of d theta, this d theta, it is called angular displacement. Similar to this example, particle moves to the point P, this is R, then moves to the point P prime, this is R prime. The difference of them, it is delta R, or called displacement. Now here, for this case, it is called angular displacement, or d theta. Also, d theta is an angle. We usually use radian for the units of the theta and d theta. Now, I want to find the angular velocity. Here we use omega to show the angular velocity. Do you know how I can find the angular velocity? Can somebody guess? Yes.
The derivative of theta with respect to time.
Exactly. Yes. The angular velocity is called omega, and since d theta is the instant with respect to time, we use omega equal to derivative of theta with respect to time. This one exactly similar to this equation. If you remember, I use v equal to dr with respect to dt. Instead of velocity, linear one, we have angular. Instead of the displacement, we have angular displacement. You will see there's similarity. Also, one more called angular acceleration. It's the change time rate of the change of angular velocity. Or alpha, it is equal to derivative of omega with respect to time. Also, we can relate them together. We have alpha and also omega, it is d theta with respect to time. From this, I can write and also d, just change the position of d theta and alpha. It is d omega divided by alpha. From this d theta, it is d theta divided by omega. I change their position. Then equal left-hand side, or equal d omega with respect to alpha, it is equal to d theta divided by omega. This by this multiply will be this equation. On this equation, as you can see, there is no time. Now, this slide also, what I do on the previous one, it shows and also confirms a straight line motion or a linear motion with angular motion. Instead of velocity, we have angular velocity. Yes, d theta. Here we have acceleration. Now we have alpha. This one is the second derivative. Also, this one is second derivative. And this is the kind of the similarity of the straight line motion with the angular pretty much. Any questions? Let's solve examples. Did you want to take a picture? Fine. I posted the notes. But if you want to take a picture, it's okay. One example, this one also is one application regarding a kind of aerospace. This is a rotor of jet engine. We consider this one as a rigid body. Now, it is rotating with 10,000 RPM. It's a revolution per minute. When the field is shut off and the angular acceleration is related to the omega using this equation, where omega is rotor angular velocity in radian per second, how long does it take that rotor to slow to 1,000 RPM? If you want to write, also think about this problem. From this one, I want to find the angular velocity. Let's start to solve this problem. Now, for this one, it's a jet engine. I consider the jet engine as a rigid body. the initial rotation speed, you will see this is a type of speed. It's, because it's rotating, is called angular velocity, omega 0. It is 10,000 RPM, revolution per minute. Now, I want to convert RPM to the radius per second. One revolution per minute, if I multiply 1 minute, it is 60 seconds. And also, one revolution, it is 2 pi radian. Now, if you cancel this by this by this, means I have one revolution per minute, it is 2 pi over 60 radian per second. Now, this one also, it is equal to 10,000 multiplied by 2 pi over 60. If I'm just round this one correctly. It is 1047.2 radian per second. Now, alpha Z is related using this equation. For example, I can substitute omega at initial speed to this one to find the initial omega, or initial alpha, or angular acceleration. Also, we want to find how long does it take. We are looking for to find time that the rotor is slow to the omega of the 1000 RPM, or this one equal to 104.7 radian per second. If I substitute also this one into here, also I can find the angular acceleration of the rotor. But how I can find the time? Let's see. Can I move to the next slide? Using that equation that I just mentioned, alpha, it is minus 0.02 omega. What is the relation between alpha and omega? Angular acceleration and angular velocity. What is their relation? Yes?
Omega is the derivative of alpha.
Alpha is the reverse.
Oh, that's what I meant. Yeah.
Alpha, it is the derivative of omega with respect to time. Yes. Now, if I write this one here, derivative of omega with respect to time equal to minus 0.02 omega. Now, what I do here, I appear a time in here. Look, time. What I can do, just I change their place. I bring the omega one side, I bring the t to the right-hand side, means that d omega divided by omega equal to minus 0.02 dt. How I can solve this one? Take the integral on both sides. At time of the zero, the initial angular velocity is omega 0, 10,000 rpm. At the time of t that reduce the angular velocity, it is omega. Or this one, it is 1047.2 to 104.7. Derivative of omega with respect to omega divided by omega equal to this. Right-hand side of this integral is e. Is minus 0.02 pi from 0 to t. But left-hand side of this integral, we need to find the integral. How? Do you know what is the integral of the derivative of omega with respect to omega? Does anybody know? How I can find this integral? Lawrence?
Natural log?
Yes. Yes. It is the natural logarithm. This one, it is the natural logarithm of omega. For some of you, natural logarithm, it is a logarithm in base of the e. For your reference, to remember you. Now, this one, it is the natural logarithm of omega from 1047.2 to 104.7. If I do this one, it is natural logarithm of the 104.7 minus natural logarithm. I just substitute 1047.2 equal to minus 0.02 t. Now let's calculate. If we calculate it, it will be time 115.1 second. This is the answer. It means that it takes 115 seconds or 115 seconds to this jet engine reduce the angular velocity of the rotor from 10,000 RPM to 1,000 RPM. Any questions? No? No questions? Okay. One announcement, do not just close your books. I have one more slide before you do that one. The homework 7, tonight is the deadline for the homework 6. Okay? Homework 7 already I uploaded in the lab. When you upload your homework 6, please be careful not to upload homework 6 in homework 7. Okay. Then due date for the homework 6 is 2/9, and also for the homework 7, I just gave you 3 questions regarding the conservation of the energy, the spring, and also those rates. The deadline will be on next Monday night. That's I want you to remember me during the week. And not saying anything. Okay. Any questions? Scan this barcode. Tell me what you learned, what you do not learn, and what do you expect to explain more on next session. When you complete it and finish your submission, I want to appreciate it and have a wonderful weekend. Please study during the weekend because next week we will have exam, and see you on next Monday. Yes? Doesn't work?
Would you listen to that, just do Monday, March 5th is Thursday?
Monday. Just let me check. Sorry, it might be the time is not. Monday, yeah, sorry. Monday is 2nd, right? Thank you. Oh, go to next.